Hello, everyone. We are picking up where we left off with climate. So, we are starting on this slide of the climate PowerPoint. Before, we had talked about more like how climate change can be measured with oxygen isotopes. That was the bulk of the lecture. Moving forward, we're going to talk about the energy budget and how we get energy and light in our atmosphere. So, all of our light that we get, all of the energy that we get comes from solar radiation. 100% of it comes from the sun. Now, solar radiation is mostly shortwave radiation, which is what we know as visible light. Long wave radiation is also called infrared. So you'll see that long wave radiation and infrared radiation are interchangeable, and I'll use both terminology in my quizzes and in this lecture and in the PowerPoints, and even in your book, it switches between the two. Now, long wave radiation or infrared radiation is given off by objects when they're trying to cool down. So that's how like night vision goggles work, right? It's only picking up on the infrared radiation in the middle of, a dark room. Things will give off heat when they're trying to cool down. So your bodies are constantly giving off heat to try to cool down. Objects are constantly giving off heat trying to cool down. It just varies per object exactly how much infrared is being given off and how much shortwave radiation was absorbed by that. And we'll get into this details of like how much shortwave radiation is absorbed versus the long wave radiation that is output. So like I said, this is a very simplified version of this image is a simplified version of what the solar budget is. But 100% of the energy into our atmosphere comes from the sun as shortwave radiation. Okay, so then once that hits into our atmosphere, there's different ways that it all breaks down. You'll see that 50% of that 100% that comes from the sun is what actually is able to touch the ground, right? And then the rest kind of gets absorbed or reflected or just kind of scattered, right? It kind of gets lost in the atmosphere, bounces around, and clouds help with that. But about 50% comes down and hits the Earth's surface. Now, that's the part that's really important. The part that comes down and hits the Earth's surface, because whatever hits the Earth's surface coming from the sun, all of that radiation is what's heating up the ground itself. So, when you go out on a hot day, the asphalt's really hot. That's only 50% of the solar radiation. If 100% of the solar radiation was able to make it down and hit the actual Earth's surface, then, that would get a lot hotter, obviously. Now, as the Earth's surface heats up due to 50% of the solar radiation coming down, it's going to want to cool down, right? Just like I said on the last slide, any object, living things or non-living things, when they heat up, when they're trying to cool down, they emit long wave radiation. So long wave radiation is that infrared radiation, right? So like night vision goggles, people glow a lot more than a table because they give off a lot more heat than inanimate objects, right? But the point here is that as things heat up, they give off long wave radiation in an effort to cool down. Now, as they're trying to cool down, right, every object has an albedo. An albedo is defined as the total radiation reflected by a surface. So that means that if something with a high albedo is going to be very reflective. So think of ice. Ice is very, very reflective. Sometimes it can even hurt your eyes on a sunny day if you're like up somewhere where there's snow. And compare that to asphalt, which has a very low albedo, right? It doesn't really reflect much. It absorbs a lot of the heat. That's why asphalt gets really warm on summer days, right? Where ice is reflecting, so it has a high albedo. Now I pose this question, do you think water has a high albedo? Most people say, yes, it's pretty reflective. If you think of the ocean surface, it reflects a lot. It actually does not have a high albedo. You're right, there is reflection on the surface, but water is something that is very unique in that it has a low albedo because it absorbs a lot of heat, but with really little variation in its temperature. This has to do with the atomic structure of how H2O is binded, how the hydrogen binds to the oxygen. It allows for there to be a lot of heat that comes in, but very little temperature change. So that's why it takes a lot of energy to boil a pot of water. It takes a lot of heat for there to be any change in the temperature, right? So water is the kind of only exception where you go, oh, it's shiny, but it doesn't have a high albedo. A good way to think of this is when you go to the beach on a hot day, you're walking through the sand, and that sand is typically very hot, right? It's burning the bottom of your feet. And then you get into the water and it's pretty cold, right? The same sun is hitting the sand that's hitting the water. The difference is one has a high albedo and one has a low albedo, right? So the water is really absorbing the lot of heat. All right, so here I said this on the last lecture too, but just for note's sake, the following slides where I talk about the energy budget, in the notes section of each slide, there are notes of me explaining what you need to know. There is more information in the notes that you need than you need. So if there's something that you're reading that you're like, I don't remember Tina talking about that, then you probably don't need to know it. Okay, so you can sort of skim right through that. All right, so Earth's energy budget. There's a lot going on this image, right? So we're going to break it down. Here it says 100% of the energy into the Earth's atmosphere comes from solar radiation, comes from the sun. Now it's broken up into all of this random stuff. Now, generally speaking, you'll see 100% comes in, and like I said before, roughly 50% gets absorbed by the surface, right? Gets absorbed by water and land, and then the rest of that gets scattered. It gets reflected, it gets, absorbed by clouds or reflected by clouds, right? It's just getting scattered all over the place. It's not really making a big difference in terms of how the Earth gets heated. And that's kind of what I'm highlighting here. You'll see that about 30% of it just goes right back out into space, right? It's just almost like wasted energy. And then about 20% of it gets absorbed by clouds or by greenhouse gases and things like that. And then about 50% of it gets absorbed by water and by land. Now, if we look at the outgoing, which is this 100% here, all right, so it's broken up. Whatever is escaping Earth's atmosphere, that is going to be broken down a little bit differently than what is as simple as what's coming in. So as it escapes, we have about 30%, like we said here, getting scattered right back out. But then down here, where it says sensible heat and latent heat, I define what those are in the notes. You don't need to know those definitions, but it's essentially the energy that it takes for water to turn into water vapor and be put into the atmosphere. So that's an energy exchange, right? And that energy has to go somewhere. And so that energy goes into the atmosphere, which is, energy is another word for heat. So you have about 30% of the heat going right back into the atmosphere because water is trying to cool down since it's absorbed 50% of the solar radiation. Now, one thing to note, remember, is that when things cool off, they're giving off infrared radiation and not solar radiation. Now, greenhouse gases like water vapor, carbon dioxide, those, methane, all of the greenhouse gases, those aren't the only three, they only absorb infrared radiation. They do not absorb solar radiation. So the sun goes right through greenhouse gases. However, when things try to cool off on our surface, they are giving off infrared, and that gets trapped by the greenhouse gases. The specific wavelength of an infrared radiation doesn't really get along with the greenhouse gases, so it acts as a barrier and it traps it. So you're going to see that here, right? Net emission, surface emission of long wave radiation, and then you'll see that it gets absorbed by water vapor and CO2, which are greenhouse gases. And then you'll see that the rest of it is getting emitted right back out into space. So some of it does get to escape and go into space, but a big majority of it gets trapped here in our atmosphere. And you'll see that this dashed line is just showing you below it is our atmosphere and above it is space. It's labeled here. All right, so this stuff down here is getting trapped, and then some of it is escaping. Okay. Now, the important thing is that the greenhouse gases only absorb the solar or the infrared radiation. So the Earth's surface gets heated up by solar radiation that comes down, right? The sun heats the Earth's surface, but then the Earth's surface is trying to cool down. And as it's cooling down, it's giving off the infrared, and then the greenhouse gases trap that infrared radiation. So what that means is that we don't actually get hot from the sun. People think that the atmosphere gets warmer because of the sun's rays coming in. It's actually not true. We get warm from the bottom up. So we get warm starting at our Earth's surface, moving up towards space. So sun's radiation comes in and heats up the surface, and then the radiation that's given off by the surface is what actually heats up the entire atmosphere. Right? So the heat's not coming from above, the heat's coming from the surface of the Earth. Right? So that's one big misconception that people have. Now those the greenhouse gases, there's more than three. These are the three most common ones and the most voluminous ones, meaning that they're the most prevalent. The first one by far is water vapor. Now water vapor is given off by steam. There's clouds, evaporation of the ocean water, of any sort of lake water, river water, standing water. All right, so that gets put into our atmosphere as water vapor. The second most common one is carbon dioxide, which I'm sure you've heard of by now. Right? We know carbon dioxide is produced by you breathing. It's produced by cars. It's produced by any factory. It's a big byproduct of a lot of the stuff we know in our Western society. And then the third one is methane. Now, methane is produced through the same things that produce carbon dioxide, so gas and oil, factories, things like that. But another big producer of methane is cows. Okay? And we'll talk about that a little bit. So like I said, greenhouse gases are only absorbing the long wave energy. The sunlight passes right through them. And those gases are acting as a blanket. They insulate the Earth, right? So the atmosphere is covered with this blanket of greenhouse gases, which is very important because if we didn't have greenhouse gases, the atmosphere wouldn't be suitable for us to breathe, right? And it wouldn't be the right temperature either. So they're necessary, right? Greenhouse gases are an important aspect of our atmosphere. So they're just a little bit out of control right now, right? So why is everyone so worried about them? Because this is the most we've ever seen of them from what we can track in human history. We have never seen this much carbon dioxide, methane, or water vapor in our atmosphere. Therefore, we have never seen temperature spikes the way that we see them today. Right? So that's why everybody is concerned, right? It's not that the Earth wouldn't be able to handle it or something like that. We've just never experienced it before, and it's happening at such a fast rate that people don't really have an answer for how it's happening and what to do once it does happen. So the more greenhouse gases we have, right, that's our blanket on the Earth. That means the more insulation we have, which means that the more heat is kept closer to our Earth's surface. That's why we're heating up. It's like putting a thicker and thicker blanket on in the middle of summer, and you're overheating, right? That's essentially what's happening. The carbon dioxide is thought to be the main culprit of this, right? That's what you hear about all the time. And that's because it can be directly linked to temperature, right? There's all these graphs where you see carbon dioxide spikes and temperature spikes. So it's very easy to see the correlation between the two. And methane is kind of ignored, even though it's the third most significant one, right after carbon dioxide. But it's a huge component. And you'll see now that climatologists are really shifting away from carbon dioxide. Not that it's not important, but they're really learning a lot more about methane, and that we should have been paying attention to methane first. So let's talk about carbon dioxide a little bit first. So carbon dioxide, right, I've already said it's a byproduct of us breathing, of cars, of factories. It's kind of hard to avoid if you want to live in a Western society, unfortunately. For the technology we have now, it's a little bit unavoidable. But you can see that in carbon dioxide spikes, you'll see that there's a correlation in history of temperature spikes. And they're pretty much the same. And the down where the carbon dioxide decreases, that has to do with like ice ages and things like that, where carbon dioxide is locked up in ice rather than in the atmosphere, which is typically what you see in a more tropical, warm environment where you have the spike. Right? So you can really nicely link these two things together, right? It's easy for people to report this on the media, for you to see the correlation. It doesn't take much explanation. Another reason that CO2 is really focused on is because CO2, carbon dioxide, is what's causing ocean acidification. So a few years ago, we really heard a lot about ocean acidification because we started to have all of these coral reefs die off, and we were in an El Nino year, which is where things are typically warmer, and the ocean was getting too hot, and things were, living things were uncomfortable, and so a lot of things were dying off, unfortunately. And that's all linked back to too much carbon dioxide in our atmosphere. And I think on the last PowerPoints or on the last lecture, I talked about how the ocean and the atmosphere are really closely related. They kind of work symbiotically. So if something is happening in the atmosphere, it's going to affect the ocean. So if there's too much carbon dioxide in the atmosphere, it ends up getting absorbed by the ocean. And when you have water combined with carbon dioxide, it can actually produce something called carbonic acid, which causes the ocean to literally be acidic. So if you think of the ocean as having a pH of 7, let's pretend, right, which is perfectly neutral. It doesn't have that pH, but let's pretend. Ocean acidification would cause that pH to go down and become literally like acid. So it would become like a 6, pH of a 6, pH of a 6.5, and that might sound like a lot, but a lot of animals, especially living like plants, like corals, things like that, really rely on that specific pH value. So any change in it, like a 0.5 change in a pH, is very significant for those ocean animals. And so when you kill something like a coral reef or kelp or things like that, it travels the food chain pretty quickly. So things that rely on the kelp, like let's say shrimp or other fish, then these larger fish eat those shrimps and microorganisms, and then those fish no longer have a food source, so they start to die out. And then that's going to really, it's not only a bummer for those fish, but it's also a bummer for anybody who relies on that fishing industry, right? So then people go without jobs, the fishing industry kind of dwindles down a bit. And so it's really important that our ocean does not acidify. So before we move on from carbon dioxide, this is a great indicator of how much carbon dioxide are you actually putting into the atmosphere annually, and it gives you some numbers, right? So it says it's about 17,000 pounds of CO2 if you use 1,100 kilowatt hours of electricity per month. So you can go onto your bill and check what your parents' bill, if you live with your parents, what you use per month. And this is how much CO2 is getting put into the atmosphere, which is a lot. 17,000 pounds is a lot. You can see that it's the most by far, right? So electricity is a big one. That's why it's important to like turn off your lights and things like that. It feels like it's not a lot, but it's quite a bit. Natural gas a month, if you use 2,300 cubic feet of natural gas per month, you're putting about 8,800 pounds of CO2. So natural gas is about half as much as electricity per month, right? So that's why a lot of people will switch to natural gas if they can. 4.5 pounds of trash a day will emit about 1,000 pounds of CO2. And trash is a big contributor, not only for CO2, but for methane. A lot of dump sites put out a lot of methane, and composting is becoming a very popular thing now, because if you remove the organic materials like your banana peels, whatever's left over from your meals, leftovers that you throw in the trash, if you put that into a separate container so it's not mixing with plastic and whatever other trash you have, it won't put out as much methane. When you have organic material mixing with non-organic material, this is when you start to create a lot of CO2 and a lot of methane. So that's why composting has become such a big thing, to actually separate those materials out so they don't all sit at the dump together, right? In an effort to be a little bit cleaner and have a smaller carbon footprint. If you drive 160 miles a week, you're putting out about 8,900 pounds of CO2, which is, that's quite a bit. 160 miles per week is putting out as much CO2 as what you would use of natural gas per month. So 160 miles is not that much, in all honesty. You probably drive 160 miles per week, especially in California where everybody drives. It's not like we have public transportation. So that's why it's a big contributor to CO2. And then flying is about 1,000 pounds of CO2 if you fly 1,900 miles a year. 1,900 miles, it's not that much. This, you'll see, you'll do a carbon footprint sort of test just to see where you're at. You'll take a little quiz, and you'll see how large or how small your carbon footprint is. If you're someone who flies a lot, then you'll see your carbon footprint really increases dramatically. Flying is not the best mode of transportation, but it is hard to avoid. So that was all about carbon dioxide, but see, we really need to kind of shift our focus to methane. So we're going to talk about methane, and very little people know much about methane and how it behaves as a greenhouse gas. So methane was released into the atmosphere due to oil and gas industry, of course. Anything that produces carbon dioxide usually also produces methane. So they kind of go hand in hand. However, the dairy and meat industry is an industry that doesn't produce carbon dioxide, but actually does produce a lot of methane. So methane is 30 times more potent than carbon dioxide. What I mean by more potent is that it does more damage when it's around. So if you have one molecule of carbon dioxide, or one molecule of methane, it is the equivalent of having 30 molecules of carbon dioxide in the atmosphere. So you need 30 times less methane to do as much damage as carbon dioxide. So very little goes a long way. It's kind of like a heavy hitter. A little bit of methane is going to do a lot of damage. One thing to know is that the half-life of carbon dioxide is a lot longer. I think it's about 100 years. So it stays in the atmosphere longer, while methane is like 10 years. So people used to argue, well, methane's only around for 10 years. How much harm can it do? But what we've actually seen is that the damage it does in 10 years bypasses the damage carbon dioxide does in 100 years by threefold. Okay, so methane is really, it's like once it's there, it's doing a lot of harm. So I went to a climatologist talk recently, and he was just giving new data that we have, and we were keeping up to date on everything. And the thing that they said, and that most climatologists agree, and you might have heard this as well from different articles and things like that on the news, the number one thing you can do to become more environmentally friendly is decrease meat and dairy intake. So meat and dairy intake, the way that we farm now in America, where we mass produce, really produces a lot of methane. And it's not that meat and dairy are bad. I'm not here to take a stand on whether you should be vegetarian or vegan. I'm just giving you the facts of the way that things run now. The problem environmentally is that it produces so much methane that it's really hard to make an argument of why it's good, right? So here's some comparisons to show you. Each year, 2 cows, which is what this image is showing you, traps as much heat as one car that was driven 10,000 miles. So most people drive 12 to 15,000 miles a year, and 10,000 miles, so let's say that's 3/4 of a year. So 2 cows produce as much harm to the environment as you driving your car for 3/4 of a year. Right? So that's why it's such a heavy hitter, right? Like here it says it's only 504 pounds of methane. However, the carbon dioxide equivalent of that is almost 12,000 pounds. Right? So here I say, however, the average American isn't aware of the impact of their dinner choices makes on the environment. Why do you think that is? Right? So most people don't understand how much the meat and dairy industry mess with our environment, right? People don't really think about their food and having a connection to the environment. People just recently started thinking about how food has an impact on their health, right? And now that's kind of like the whole trend, trying to be healthy, that sort of thing. But now we're seeing that meat and dairy, or any of your food, right, can be really closely linked to what's happening in our environment. There are ways to farm and produce meat and dairy where you actually don't produce any methane. It's more expensive to do that, and it would take rearranging of all of our systems that we have in place, but it's possible. Right? You can still farm cows and pigs and chickens and have a negative methane output. Actually, you can become a carbon sink. That's what it's called when you have a negative carbon dioxide or methane output. You call it a carbon sink. So the counter argument of why, oh, I never answered the question of why do you think Americans don't know the impact of their dinner? There's several theories, and you have a question on this, I believe, in one of your assignments, of why, speculating why we don't know about this. So maybe I won't answer it, but it's important to think about politics when it comes to stuff like this. How does this affect the overall economy? How does that affect, the news outlets? How does it affect farmers? Also, it could just be being naive. We just started to figure this out a few years ago, and so the word might have not gone out yet. Now, the counter argument of why methane is not as bad as carbon dioxide, like I said before, it doesn't last as long as carbon dioxide. However, like I said, the truth is that when that greenhouse gas is around, when methane is around, it does the most damage when it's here compared to carbon dioxide. It does 30 times more damage. So that's really the issue. So when we talked about that graph earlier, about how carbon dioxide and temperatures can be closely linked like this on a graph, right? This graph ended in 2007 and it's more than 10 years later, so we're a lot higher now. One thing to note, and one thing that I mentioned earlier, is that you have these low points and then you have these high points. So climate cycles are normal for Earth. This isn't something that we haven't seen before. We're used to going up and down, up and down, up and down. However, we are heating up much faster and at higher rates than we ever have before, so it's uncharted territory. And also in that meantime, it's not only that we're heating up so quickly, you can kind of go, okay, so what? We're heating up fast, like the Earth can take it, it's going to be fine. It's that things are dying off because we're heating so quickly, and so obviously it's having a negative impact in terms of what gets to live and what doesn't. Right, so it's also an issue because we can't cool down as fast as we're heating up. So even if we skyrocketed, but we knew we could drop really low, it might not be that much of an issue. But we don't know that. We don't know that we can drop down low to here where we've been in the past. Right? We don't actually know if we can get back down there. You can see that the variation is roughly the same over the last 300,000 years that we know of. So we don't know if when this drops down, is it going to be able to drop down here, or is now the new low all the way up here, which would mean that we're constantly hot. Now for the natural causes of climate change, so before, when we have these ups and downs, these are all caused by natural sources. At this point, we really didn't have, anything that would cause a great export of carbon dioxide into our atmosphere. So these were all natural cycles. And the reason we had natural cycles is because mostly of something we call the Milankovitch cycles. So the Milankovitch cycles are these astronomical changes in Earth's position. So you can have Earth change its orbit, you can have Earth change its axial tilt, and you can have the Earth's wobble change a bit. So I'm going to show you pictures of what that means. But these all change at a specific interval, and when they do change, you'll see that we change climate quite a bit. Another thing to think about is the position of our tectonic plates, right? So if you have climate near the equator and then your tectonic plate moves towards the poles, that's going to be a totally different climate. So that can also cause natural climate change. So when we're talking about these Milankovitch cycles, Milankovitch was a scientist. The orbital change is this photo here, right? It's how close or far are we getting from the sun. So we fluctuate between this more circular orbit and this more sort of oval orbit. You can see with the more oval, we go farther from the sun, but then we kind of come closer over here, right? So we have the two extremes. Now with the more circular one, we go pretty far from the sun, and we're kind of far from the sun for most of it, except for right around here. So we fluctuate between these two positions every roughly 100,000 years, and it's a slow transition, right? We'll kind of make our way out, and then we'll make our way back in. It's not all of a sudden we're bouncing, this far out into space. So over 100,000 years, you shift between these two positions, and because you're closer or farther from the sun, that's naturally going to change the climate. Now, axial tilt, that happens about every 40,000 years, 40 to 41. And that's how much are we tilting towards or away from the sun. Right? And this degree change, I think it's only a fluctuation of 1 degree. It's like 23.5 to 24.5. So it's not a huge huge change, but it's enough to change the climate and where the sun is pointing to the earth. Now with wobble, the earth does wobble a little bit. So you can see that it's going in this like circular motion, right? So depending on where we are in this circular position, right, and it is wobbling on this axial plane, which is the center. So it's like kind of wobbling around the center point. Where we are in this, right, is going to be changing about every 26,000 years. So we're kind of moving along this circle, right? And how this is going to dictate again how close or far we are from the sun. So all of these changes are kind of constantly occurring over the course of these 100,000 years, right? So every 100,000 years, you're going to kind of end up back at the same orbit. But these changes are causing these natural cycles. So you're going to naturally have more carbon dioxide and then less, and then more and then less. So, right, so during warmer climates, you're going to have more carbon dioxide. During colder climates, you're going to have less. And that's going to be all dictated by these cycles. Now, the Milankovitch cycles, they're actually named like eccentricity, tilt, and precision. You don't need to know that. It's okay. You just need to know like orbital tilt, axial tilt, and wobble. Orbital change, not orbital tilt, sorry. So you don't have to know their actual scientific names. You don't need to know the degrees. You just kind of need to know the motion and the names of what's changing. Okay, so that's one way we'll have natural climate change, and for the most part, really the only way we've had it in the past. All right. Hope you guys learned something really useful, and that when you hear stuff about climate and talk to your friends about climate change, that now you're a bit more informed, and you're going to take a climate quiz online that tells you what your climate score, your carbon footprint is, and it's really interesting to see where you stand, and just take it as an educational step. And you know, when I ask you what's one way you can change your carbon footprint and reduce your carbon footprint, and I hope that you use what I've taught you in this lecture to really think about and evaluate your own life, and what are the small baby steps that you can do to sort of make our earth a better place to be for future generations. All right, you guys, talk soon.